Discuss a very brief topic today, balancing redox ionic equations. In an ionic equation, what you're actually doing is, these are often referred to as net ionic equations. You're kind of focusing on the species of interest. So we could actually take a reaction such as the magnesium oxide and iron reaction that we have looked at before. Magnesium is one of our charges that's changing, as well as iron. So if we go through and we assign our oxidation states to each of these, what's really happening here is magnesium is going from a +2 to a 0, it's getting reduced, and iron is being oxidized, going from a charge of 0 to a charge of +3. Throughout this reaction, oxygen stays -2. Oxygen is something that we could call a spectator ion. So we can actually go and we can write an ionic version of this equation, where we write Mg plus 2 plus Fe makes Fe plus 3 plus Mg. At first glance, this might appear to be balanced to you. You have 1 Mg on each side, you have 1 Fe on each side. But it's actually not balanced because it's not balanced for charge. So because we have a +2 on the left side and a +3 on the right side, this is only balanced for mass. It is not balanced for charge. And we need to balance our reactions for charge as well. So if you're given an ionic equation, and typically the way you would be given this is what you see up here, where it's very hard to balance this based on mass because, or actually not possible, because you're not given that spectator ion, that oxygen, that actually is what would help you balance that in the first place. So in order to balance this, we're going to actually go and write oxidation and reduction half reactions. So our magnesium, oops, I'm sorry, that's actually our reduction. Our iron is going from a charge of iron 0 to a charge of iron plus 3. And it is doing so by losing 3 electrons. Our reduction is our magnesium plus 2 becoming magnesium 0. And this is happening by the gain of 2 electrons. We kind of talked about this before, the fact that this number and this number have to be equal to each other. So in order to get those two numbers to be equal to each other, we have to find a common multiple. So the only thing that we can do to get a whole number of electron, or a whole number of moles of electrons, is to multiply our entire oxidation by 2. That will change this into a 6. We'll put a 2 here and a 2 here. Our reduction, we're going to multiply everything by 3. So it's 6 electrons here, 3 for magnesium, 3 for magnesium. And what that actually tells me is that back up in my reaction, I should have all along had a 3 in front of magnesium, and I should have all along had a 2 in front of iron. There is a little bit of a shortcut way of doing this. Very often you can use kind of a little reverse crisscross trick here. So if you look at the aluminum having a +3 here, actually means we're going to end up putting 3's in front of the coppers. This copper is a 1, which means aluminum is going to end up with a +3, or a 3 in front of it, sorry. I'm going to actually prove this to you by doing half reactions. So Al plus 3 turns into Al0, and this occurs when aluminum plus 3, gains 3 electrons. Copper 0 is going to turn into copper plus 1 by losing an electron. Aluminum needs to be able to gain 3, so copper losing 1 isn't going to cut it. So we're going to go through and we're going to multiply everything by 3, and this now makes our electrons add up. So what this does for us is we end up with 3's in front of our copper, which relate to this 3 right here. This is kind of like a weird reverse crisscross trick. So this 3 with aluminum tells me I should put a 3 there, and it tells me I should put a 3 there. So if I do it on one side, I got to do it on the other one. The 1 with copper is telling me to put 1's with my aluminum, which I have 1's here. And again, you could leave those blank. I have 1's in my aluminum half reaction, and I have 3's in front of copper in my copper half reaction. Another thing that you have to actually identify is the number of moles of electrons involved. How many moles of electrons are being transferred here? 3 moles of electrons. So 3 moles of electrons are being lost by copper and being gained by aluminum. You do have to be careful with that trick, though. I'm going to show you one example where you have to remember to reduce. So in our next example, because calcium has a +2 with it, that clues me in to these sodiums probably needing 2's with them. Because sodium has 1 here, I can probably leave my calcium as +1s. So I'm going to go ahead and write a couple half reactions to prove this. If I write these two half reactions, without the 2 with the sodium, I only have this 1 electron over here when I really need it to be 2, like it is in the calcium reaction. So I would go through, and in order to make those, match up, be the least common multiple, I'm going to multiply everything by 2. So that agrees with the fact that I had to put 2's in front of those sodiums in the reaction. And I have 2 moles of electrons being transferred. I'm going to have you try the next 2 on your own. Please keep in mind I did throw a little trick at you on the last one. So pause this for a minute and try these 2 reactions. So if we wanted to work these out, because of the 2 with copper, I'm going to put a 2 in front of each nobelium. Because of the +5 with nobelium, I'm going to put 5's in front of my copper. To check how this balances out, if I did Cu +2 turning into Cu0, that happened by the addition of 2 electrons. My nobelium 0 became nobelium +5 by losing 5 electrons. In order to make those numbers of electrons agree, I'm going to have to multiply everything in my copper equation by 5. That will give me 10 electrons here, 5 here, and 5 here. My nobelium equation, I'm multiplying everything by 2. Gives me my 10 electrons here, 2 here, 2 here. So that agrees with my numbers back in the equation, and I am transferring 10 moles of electrons. Now, the next one's got a little trick in it because you do have to reduce this to a lowest whole number ratio. So what you initially would do is say, okay, chromium's got that 6 with it right there. That means I'm going to put 6 in front of my tins. This 4 tells me I'm going to put 4's right here. The problem with this is not a lowest whole number ratio. So we actually want to reduce all of these. We're going to divide all of them by 2. So instead of 6, 4, 6, 4, we're going to end up with 3, 2, 3, 2. And let's check this out and make sure this works. So our tin +4 changed into normal tin when it gained 4 electrons. Our chromium 0 changed into chromium +6 when it lost 6 electrons. So what I actually have here for my lowest common multiple of the 2 of these, I want to end up with 12 moles of electrons. So I'm going to multiply my tin equation by 3, which will give me 12 electrons here, 3 and 3. And I'm going to multiply my chromium equation by 2, 12 electrons, 2 chromiums here, 2 chromiums here. So those agree with my numbers in the equation. You wouldn't fully be wrong to have those higher numbers that we initially had, but when we correctly balance something, we are required to have our subscript or our coefficients in the lowest whole number ratio. And if you were asked about how many moles of electrons were involved, you would actually have to say 12 moles of electrons. If you do this without reducing it, you're going to look like you're transferring 24, when that's not really true when we reduce this to the lowest whole number ratio.